So any question you have to ask?
Yes, sir.
Regarding assignment 1?
Yes, sir.
Yes.
For confined concrete,
Yes.
we have to calculate for accumulator movement, calculate the water from the curve.
Right.
And how we get the curve under area under the curve.
So for for confined concrete, I have given you the equation of the stress strain curve, okay, between F and epsilon. Okay, you can integrate that. That is one. Secondly, I have given you this value. We call it epsilon CC. Okay, and this peak stress also. What you can do is, this you can assume to be parabolic and take 2/3 of this rectangle, and this you can assume linear, and you can calculate this as tabular. So that is simple. Actually, when you will be doing a computer programming, you can take strips and use the trapezoidal rule to integrate.
The strain value is less than epsilon cc, so we have to integrate the
But when are you having that case? Epsilon cc, less than epsilon cc, in which case you will have? That will be happening if you are plotting different points on the curve. Okay. But when you are calculating mu, then actually it will be up to epsilon u. So you will be needing the complete curve. Okay. To calculate mu and phi. Below this, I told you what you have to obtain is actually my dash and phi by dash. And up to my dash and phi by dash, both curves for confined and confined concrete can be taken as same. Any other doubt? Any other question? No? That means you have not yet started. Okay. So I know you will wait till last day and then there will be problem. Then you will not be able to do it. Okay. So if you are not starting it sufficiently early, you will not be able to do it. Okay. Because you will have many issues. I can tell you step by step also. Okay. But then you will learn in that class and then forget. I want you to remember those. Those should be clear in your mind. So until unless you are doing yourself, making error and then correcting it, you will not learn. So for that you have to give time. Start working on that. Okay. So then we will continue what we were discussing. First, we considered a cantilever. Okay. And we have drawn m versus theta or p versus delta or q versus delta rather. We represent it by q and axial load we represent by p. So we can develop this curve, either monotonic or cyclic backbone. This type of curve we can obtain. These values we can obtain from AC 41, and this value, how we are going to obtain this? I am not giving these values. How we are going to obtain that? This is my and this is theta y. A and B are beyond theta y. So how you will obtain my and theta y? From section M. So my, you will first get my dash. Okay. You will divide it by 0.75 or you calculate the moment capacity at concrete strain of 0.04. Okay. So this my you can also take as M 0.0. double 0. Okay, and how to calculate corresponding theta y? Divided by what? XU. What is XU? mu divided by XU. You will
No. That's strain divided by the depth of the impedance.
Okay, but that doesn't mean that when you are taking m 0.004 that this is on the curve. Okay, so strain corresponding to that is not going to give you theta y. So first you calculate phi y. How you will calculate phi y? My divided by EI effective. That will give you the curvature at yield. Okay, how to get EI effective? Again, table is there. Depending on the axial force value, P, you can calculate EI effective. I have given you the table, I have shown you the other table in AC 41 yesterday. So you will get EI effective. This will give phi y. And then how much will be theta y? Phi y L square by
Other than this, you can use the first CV point to get this
yes.
effective.
Alternatively, you calculate my dash and phi y dash from analysis. Okay, this is alternative. My dash and phi y dash, and then you can calculate phi y as phi y dash divided by 0.75. Okay, and then theta y using the same equation. Till yield point, or what we call this point as B in our generalized notation of backbone curve. So till point B, there is no difference in monotonic and cyclic. Okay, because it is the elastic range. So here, monotonic or cyclic are cyclic backbone curves are same. Okay, difference will occur beyond B. And what is the difference occurring? The strength is reducing and ductility is reducing. Okay. In addition to that, there is reduction in stiffness and pinching. In this curve, we cannot take into account cyclic degradation of stiffness. Okay. Stiffness reduction due to cracking is one thing which we have considered here through EI effect. Okay. But due to cyclic load, cracking, closing again and again, and yielding of steel, okay, that will cause cyclic degradation of stiffness. Stiffness in different cycles will also go on decreasing. Beyond point B, cycles up to point B, it is elastic, it will remain same. So cyclic degradation and pinching we cannot represent in this curve, but we can represent degradation of strength and ductility due to cyclic behavior. If we take envelope of hysteretic response of this candidate. Okay, so you recall up to this point, we are only repeating what we have done. Then from here we can move to this case. So if I have to plot Q versus delta for this case, that will also be same. But what will be these values? Can you tell me? let me call it by some other symbol, A1, B1, because A and B we have used for cantilever. And this is QY and delta. So can you tell me how much is QY in this case? Well, how is delta Y? 5 by
X square by 6.
L square by 6. How to obtain 5y? Same as we have done in the previous case. Either my over ei factor or my divided by 0.00, sorry, my divided by 0.75. Okay. How much will be A1? A1 is plastic deformation. So when this is occurring A, this will be A1. So how much will be A1? What was A in the previous case? When we have plotted tan theta curve, we have seen AC41. So what was A? A was plastic rotation in radian. So some rotation, plastic rotation is occurring here. So if this is A wave, okay, actually first it will be elastic and then plastic rotation will occur. So I have not shown the elastic part. I have shown schematically that if this is A, how much will be A1? A12. And how much will be B1? Same. If this rotation increases to B, this is B. So how much will be this one? B12. Simple geometry. Analysis we have done only of a section. Okay, or we have done testing of a cantilever column or cantilever beam. Using that, we can get the load displacement behavior of this beam. Fixed.
Sir,
Yes.
the A shown in this column is the theta, and A1 is the displacement at the end point.
Yes, because earlier we have plotted m versus theta, here we are plotting q versus delta. So only thing is that rotation, which is actually chord rotation, we are converting into displacement. And the relationship between chord rotation and displacement is what? You can see from the geometry. So it is simply chord rotation times L. Okay?
Sir,
Yes.
I have a doubt.
Please ask.
This A1 corresponds to the displacement with respect to plastic.
Right.
Plastic movement.
Right.
So the end point of this A.
Just hold on. I have done one simplification here. I was expecting that you people will have some problem with that. Let me do it again. Okay. So what is this? This is theta pi. Okay. And how much is this? This is delta. Yield is occurring at this point. Okay. Then after yielding, what happens? The hinges form here. What will happen beyond that?
body rotation.
Rigid body rotation. So deformed shape will be like this only.
Yes.
The whole thing will deform further. So that this additional angle here, this is A. And then this is A1. What will happen further? It will deform further so that this additional angle from here, this is B, and this is, no, this total angle which we are getting from here, this is B, okay, so B is the total angle, and from here to here, this is B.
Okay, so my doubt is.
Yes, now you ask.
Yes. In the section analysis, we just read about the 2 points, means field and ultimate after the origin. So, what does that point correspond to? Means the ending point of
ending
A1.
point. Okay. So
This
this
is
is
ultimate point.
this is A, this is B, this is C, this is D, this is E. Actually, in monotonic analysis, which we have done in class, you can't get strength degradation.
Yes.
So the curve you will get there will be something like this.
Yes.
But if you do experiment, then you will get a behavioral envelope like this
For cycling.
for cyclic. So in case of cyclic load, we will get an envelope like this. Whereas in monotonic, it will simply continue up to ultimate failure. So this degradation comes from cyclic behavior. So if we are considering cyclic behavior, we will get A1 and B1. If we are doing monotonic, we will get only B1.
Yes, that's what I'm asking.
Yeah.
Means by just doing the analytical calculations, we can get the B1 only. We cannot.
Not exactly even B1, because what we will get there in monotonic will be even higher than this. So this delta U which we are getting there, that is larger than delta Y plus U. Because the failure point due to low cycle fatigue have also come closer. Okay, so the curvature at which we are getting failure, okay, under monotonic loading, that is longer.
Yes.
Okay, when you will subject it to cyclic loading,
It will converge.
it will reduce, it will fail much earlier. Okay, because steel is going to fail at lower strain now. You have seen under cyclic load, the first initial lectures, we discussed that if it is subjected to cyclic load, it will fail at lower strain. Okay, so under cyclic load, our steel is going to fail at lower strain. If you are doing monotonic analysis, then you will predict, because there we are not considering cyclic waves. Okay, you will predict high. So in experiment, you will get A1 and B1. Theoretically, you will get, if you are doing monotonic analysis, you will get high.
Okay, so A1 and B1 can.
A1 and
be
B1 will come from
estimated.
experiment. So from AC40. Okay. Any other doubt?
Sir,
Yes.
when this coil is rotated up to theta y, then that rotation delta equal to theta A into L. That should be from origin. You are
No, it is not from origin. It is from here. You see.
Why?
A1 is from here.
Because from
We have defined it like this. The A1 we have defined as A. Let's go back. What was A here? A is when it is deforming like this, still it is elastic. The moment here is my. Okay, and if you join this chord angle is A. No, sorry. This chord angle is theta. When it is my, this chord angle is theta. When you deform it further, when my has already reached, then what will happen? It will rotate as a rigid body. And this is A. Not that.
oh, that will
This angle is A. A is angle. in radian. So this angle is. So A we are measuring when yielding of our cantilever has started. Beyond that, after yielding.
That A is not from
Origin.
initial chord.
No.
That is from after yielding new chord.
After yielding, the additional angle. Till that, it is theta y.
Okay. And sir, for B also, we are measuring from that new chord where yielding is.
B also we are measuring from here, from the same point, from where we are measuring A. So B is also measured from here. So this is. Yes.
So this A value.
Yes.
So cantilever B and this they would be the same.
So what is A? A is m versus theta. So moment versus rotation. Okay. So rotation value will remain same because what is plastic rotation? Plastic rotation is occurring at a point. So whether that point is in a cantilever, that hinge here, whether it is in a cantilever or it is here, as long as the section is same, m versus phi and hence m versus theta will remain same. Because m phi depends on what? Cross section. M theta depends on what? Cross section. What is additional coming there? The plastic plane. Okay. So m theta, whether it is this or this, will remain same. That will depend only on section.
This phi y value. So both the cases will be.
What? Phi y, you have done analysis for phi y? On what parameters phi y depends? Depends only on section. So phi y depends only on section. Yes.
After point B, hinge is formed.
After point B, yes, at B yielding occurs, and after that we say that plastic
And
hinge is
rigid
formed.
body motion as well, and we get the displacement A.
Right.
And sir, after C, concrete is crushed.
Right. So strength reduces,
It reduces.
the moment capacity reduces, but it continues to deform. It will continue to deform at reduced moment. Okay. Now you can ask me, if the moment has reduced, why it is not failing here? It should fail here, because once the moment capacity, the moment it can take, suppose there is a beam, you apply a load, and the moment capacity, you go on increasing the load, and moment capacity reduces suddenly, what will happen? It will collapse there itself, in a static load. But in earthquake, what will happen? It will deform more, okay? Because in earthquake, we have discussed how much moment it can take. Moment it can take equal to its capacity only. It can't take more than moment. So the moment in our member will reduce, but it will not fail, still it can deform. Okay? So that is the difference between static load and dynamic load. Dynamic load, in case of earthquake, it is a displacement which will descend when the failure will occur. In a static load, the load will descend. As soon as the load reaches that point, it will collapse, it will fall down, because the load is more than its capacity. Up till this point, the load is increasing as per capacity. After that, either I have to reduce the load. Okay, I have to reduce the load. If the load remains same, then it will come down. It will fail. But in case of earthquake, it is not applying force. Okay, actually, it is applying displacement. And the force which this member can take will be accordingly adjusted with the rest of the stuff.
It should fail in case of static, but earthquake in reverse acceleration.
Right.
But suppose earthquake has reverse acceleration and again the intensity is more So if you collapse the whole line,
Let's take two examples. This is important to understand and visualize. It is subjected to some earthquake. It is elastic. Okay? So when it is subjected to earthquake, this displacement, elastic displacement will occur. Okay? Under earthquake, how much force will develop here? Whatever is this stiffness, K into delta. Okay? And if we are taking it angular, we can write K into delta by L. So that much moment is going to develop. Now let's say I have, let me call it ME. I have a column where the capacity I have provided here, that is only ME by 2, and I subject it to other. What is going to happen? Same earthquake I am applying, but the capacity I have provided is half. So what is going to happen? Will it collapse? What will happen? I am saying it has related. So what is going to happen?
so in this area,
Hmm?
so in this area,
No, I have just shown this section here. Let us say this is the section. Okay, here it was elastic. Elastic means what? That my section is very strong. It is not going to yield under this earthquake. Okay, so I am not worried what the section is. But here I have given some section, and that section has some capacity, My, and that My is, let us say, Me by 2. Whatever force I was getting in the elastic case, I have provided only half of it. And then I subject it to work. What is going to happen? Okay, so till this displacement continues. Okay, when it is delta E by 2, you will see it will reach M1. So at delta E by 2 itself, it will reach M1. What will happen then? Will it collapse? It will continue with plastic deformation here. Plastic rotation will occur. It will continue. Okay. How much will be this displacement? Will it be equal to delta E? More than delta E, less than delta E?
More than delta.
Hmm? Yes? You know, I have told you this in the last semester. How much will be this displacement?
More than delta.
More than delta E? Less than delta E or equal to delta E? These are the three options.
More than delta.
It is more than what we can take it equal. How we can take it equal if it is more? Huh?
More than delta.
Equal displacement principle. Equal displacement doesn't say it will be more than or equal to. So it will depend upon the period of the structure. If the period of the structure is in the velocity control range, I hope you remember what is velocity control range and displacement control range. So if the period of the structure is in velocity control range or displacement control range, that means it is a long period structure, relatively flexible structure, then this will be equal to delta E. That is interesting in case of mine. I have designed it only for half. I have provided only half of the capacity. Still, it is not failing. And displacement is also same. If this period is greater than 0.75. Suppose period is less than 0.7 second, then what will happen? This delta how much will be this?
Lesser than that.
Not less, it will be more. That is equal energy principle. Okay, it is observed. You do analysis and see. For short period structures, the displacement is more than the elastic displacement. Inelastic displacement is more than the elastic displacement. Okay, and for long period structures, equal displacement principle, and the displacement of inelastic structure is same or close. May not be exactly same, it's close. On an average, you can take it equal to. That's what equal displacement principle is. Okay, so it will come out to be the same. That is interesting about earthquake. How this happens? Same earthquake, here it is giving more displacement. Sorry, here also it is giving the same displacement. My structure is very strong. Here I have designed only half. Still I am getting the same displacement. How it is possible? What does ductility do? Energy dissipation. Because in this case, large energy dissipation takes place. Then energy dissipation takes place here also. What is the phenomenon which is causing energy dissipation here? In elastic structure, also some energy dissipation takes place. Which phenomena causes? Damping. So here damping is causing energy dissipation. Here additional energy dissipation occurs. Why? It is having damping as well as hysteresis. So hysteresis has to dissipate more energy. Okay, earthquake you can visualize as the energy given to the structure. So the structure has to dissipate that energy. If it is elastic, it will be dissipating that energy through damping alone. If it is inelastic, it will be dissipating energy with damping and hysteresis. And magic is this, that this hysteresis dissipate energy in such a way that the final displacement comes out to be same. That's the interesting.
Final displacement means?
Total displacement of this system, which I have designed for lesser capacity. The total displacement of this and this, it's same for long period. Here, this delta is greater than delta. And what is the relationship? We have done it. Can anybody tell me what will be the relationship between delta and delta E? All of you know it. We have done it in last semester. करके बताओ. If I have designed only for half ME by 2, how much is R?
1.
In this case, what is the value of R?
1. Elastic range.
अरे भाई आधे के लिए डिजाइन किया तो 1 कैसे हो जाएगा?
Mu होगा ना? Mu. Ductility.
What is R? The reduction in the capacity for which I have designed. Design capacity divided by the demand on elastic structure. So that is My divided by Me. So R is 2. For R is equal to 2, can you calculate delta of the elastic structure in terms of delta of elastic structure? That's good. I have drawn the diagram to explain equal energy principle and equal displacement principle. You will draw the diagram, then you will do it. So, for those who have not done last semester, so if I plot Q versus delta for elastic structure, the relationship will be linear. Okay, and then My or Qy, this is what I am designing for. So delta U is same as delta E. Okay, this is equal displacement T greater than 0.7 seconds. For short period structure, Q versus delta, this is the elastic structure, QE versus delta E. For inelastic structure, it will behave like this. The displacement here, this delta U is greater than delta E, and this area is equal to this area. We call it equal energy principle. T less than 0.7 seconds. Okay, and I also give you that this is R and ratio. Okay, not the distance, ratio of these two. Ratio of these two is giving you the mu, and R is equal to square root of 2 mu minus 1. This is equal displacement principle, this is equal energy principle. Equal displacement principle is valid for long period structures, and equal energy principle is valid for short period structures. This we have done in the last semester. It's revision of that. Now using this, can you tell me if this is delta E, how much is this delta U in terms of delta E? 2.5 times of delta U. Delta E. How? You have calculated mean. Delta by delta E is not mu. Keep in mind mu is delta by delta y, not delta by delta E. But you can calculate delta y in terms of delta E. How much is that? It is similar triangle. So ratio of QE and QY is same as the ratio of delta E and delta y. So delta y will be delta E by 2. It's geometry. It's not structural engineering. So can you tell me how much is this delta U in terms of delta E? Just some substitution you have to do. You know R? Yes. How much was it? You have not done this substitution. Delta y is equal to delta E. So delta E is equal to 2 times delta y. 1.25. So 25% increase will occur if my structure is short period structure as compared to elastic structure. It's not 2.5 times or 2 times of delta. It is 1.25 times of delta. Are you able to get? Everybody is able to get 1.25 delta E or not? Could you get? Vijay? Substitute R, calculate mu. It's simple. Mu is equal to how much? 1 upon 2 R square plus 1. Substitute R is equal to 2, you can get mu. Okay, then you can calculate delta U in terms of delta Y, and substitute delta Y is equal to delta E by 2. You will get it. You square it and take it this side, you will get mu. Delta mu is not 2. Mu is 1 upon 2 R square plus 1. R is 2. Delta U. Any delta, it may be ultimate or in between also. It is not delta E, it is delta. Response of the inelastic structure. So if R is equal to 2, you will get delta U as 1.25 delta E. So this is something very interesting about earthquake. I have designed it for half. If period is greater than 0.7 seconds, the displacement will remain same. It will still survive. Now suppose I reduce it to 1/4. The moment capacity which I have provided here is only ME by 4, only 1/4. Then what will happen? Then also it will be delta inelastic will be equal to delta E. Very funny, isn't it? The strength does not matter.
It is for long periods.
For long periods. For short period structure, only 25% increase in the displacement. Ductility demand will be more. Okay, so can you get something without paying anything? Here it looks like what we are paying. Strength we are able to reduce, but we must be paying something now. What we are paying? What we are paying? We are paying in terms of ductility. Okay, here my structure needs not to have any ductility. Still it will survive. Here, how much ductility my structure has to take? If it is long period, then mu has to be equal to 2. Then only it will survive. Here, the ductility has to be 4 or more. If it is short period structure, then it has to be more. Then only it will survive. Okay. So if my strength is reducing, still the structure will be able to survive, provided it has adequate ductility. Okay. This is something interesting. Now you look back here. Here what is happening? The strength is reducing. Suddenly, will it collapse? No. Ductility demand will increase. If the structure still has that much ductility capacity, it will survive. So it is not the strength which will decide failure of the structure. It is the ductility the deformation capacity B value, which will decide where our structure is collapsing. So that's why this A and B value becomes very important. Yes. You were asking.
Previous slide.
Previous slide. You mean this one?
Sir. In this, we have designed first column for ME.
I have not designed. I have just performed analysis of elastic structure.
Okay.
What does that mean? That I can provide any capacity to the section.
Okay.
Whatever earthquake will require, I will provide. That is ME.
We have provided capacity that it can go up to delta E, and after delta E it will fail. That section will fail.
No, it was not. It is elastic.
It-
Earthquake, whatever earthquake is causing, the maximum displacement which is occurring in the earthquake, there is no failure. Whatever maximum displacement is occurring during earthquake, that is delta E.
Okay. Up to delta E, that section will go up to LE.
Here there is no section. Think it like this. I have a section where strength can be anything. Whatever strength you will say, I will provide. Okay. And I am shaking it during earthquake.
Final question is that in this case,
ME is the moment demand on elastic structure. If my structure has to remain elastic,
Yes.
it doesn't yield, then how much moment will develop? That is ME. ME is not provided. ME is what earthquake will require if my structure has to remain elastic.
How can I know that? How?
By simple analysis. Take the structure, subject it to earthquake, perform analysis, linear analysis, which you have learned in the last semester. Perform that analysis. You will get the moment which is required.
Sir, question is that you are saying in this case and in this case displacement are equal, even the section capacity is reduced, even the demand is reduced.
Even if I have, demand is not reduced. I have said that even if I have designed my structure to half of the demand which was here, the capacity required was ME. I have designed only half of that what is required.
Okay.
Not that it is half of this. Okay, I have designed it for half of what is required. Okay, still it will survive, provided it has this much capacity.
Okay, sir. If the earthquake, let's consider earthquake force is coming 100 kilonewton. We have designed for this 100 kilonewton. This is for 50 kilonewton.
Right.
Even though you are saying that the displacement in this case and displacement in this case are equal,
Right.
I am saying that I am designing for this 100 kilonewton. If the 100 kilonewton is coming there, it will resist 100 kilonewton. After that 100 kilonewton, it will go in the plastic zone.
Right.
Okay.
If you apply a higher earthquake,
Higher earthquake than this.
then this will also.
Than this. Now in second case, this is earthquake 50 kilonewton.
Right.
When I apply this 100 kilonewton, it will up to 50, it will go into up to elastic range. After 50 to 100, it will go into plastic range. And
After elastic, force cannot increase. That's the difference. That's what I want to make you understand. You cannot apply 100 kilonewton force on this because it has been designed for 50. So the maximum force, that's why I said that earthquake is not applying force. Earthquake is giving energy. Earthquake is causing displacement. This thought, this thinking we have to change. That earthquake is applying a force. Earthquake cannot apply force on my structure more than what I have designed for. If you will apply 100, you can't apply. If, suppose, I have a capacity to take a weight of 50 kg. You put 100 kg on my head, what will happen?
I will simply fall down.
I can't take. So 100 cannot be applied. Okay. But still, it will be survive earthquake. Why this problem is occurring? Because you are thinking earthquake as a force. The earthquake is something which is causing 100 kilonewton force. No. Earthquake is causing force on different structures by different amount, depending on how much that structure can take. But it is causing the same amount of displacement.
Yes, sir. But while designing the structures, we have taken the ground motion data, then calculated base shear from response spectra, and that we have converted it into point loads. Then we are applying the earthquake as a point.
That's why what all we did in first semester, why we are doing the second semester. Everything we have done in the first semester. So whatever we have done in first semester, that is wrong. Okay. All that is wrong. So first I taught you in the first semester wrong things, and now I am teaching you what wrong I have taught you there. So that is an equivalent static method. Why we do that? Because our engineers understand design for force. So there we have represented it in terms of equivalent force. But in reality, earthquake does not apply force. Okay?
Then we have to think like, is some energy, some imparted by earthquake? Then I will plot through that our system from hysteresis, whatever area I will get, compare that area and that area. If this area my hysteresis to be greater than this area, then my structure will be same.
Yes. But it is not that simple. Okay? It comes. In principle, what you are saying is correct. But there are issues. Okay? So one method of earthquake resistant design is energy-based design. Okay? So one approach, one school of thought is energy-based. Okay, so there is energy-based design also. There is force-based design, which we studied in our first semester. What we are studying here is the displacement-based design. Displacement is equal. So we are studying here displacement-based design. There is energy-based design also, where you calculate the energy, what you have explained nicely, that energy imparted to the structure, and then the energy which the structure can dissipate. And if a structure can dissipate more energy than what is imparted, it will survive. If it cannot dissipate that much energy, it will fail. Okay. But there are some problems. That's why energy-based design is still not being taught. It is a developing area. People are working in research. There are some questions which have not been yet solved. Okay. So that's why we are not teaching that, because it is not in that stage. But if you want to take up research, as in your dissertation, you can take energy-based design as well. Okay, so people are working on that. So here we are talking displacement-based design. So you think it like this, that earthquake is causing a displacement. It is not causing force. It is causing displacement. Okay, that displacement remains same. If the structure is strong enough, it can resist that displacement elastically. No hysteresis required. If the structure is not having that much capacity, then it will yield, and then it will dissipate energy through hysteresis, and ductility is required. Okay. So that's what this displacement based design is, and you have to understand that in this semester we have to look at earthquake differently. You have to come out of that state of mind in which you are considering earthquake as force. Okay, actually it is not force. In reality, we have to understand earthquake cannot apply force larger than what I have designed for in my structure. Yes?
In previous semester, the force-based design is wrong, but the earthquake resistant structure which we have in India, they are all force-based design.
Yes.
Right now.
In all world, not only in India.
They have
Now, if you look ASC 7, the recent code, it has given an alternative method. So displacement-based method is being accepted in those codes as alternative method. Our codes is not accepting even this as alternative. Okay. Well knowing that that one is wrong, this is the correct one. Still. Region? You have to do this semester. Then only you will be able to do it. Okay. So if you learn this displacement-based design, then only you will be able to do it. Okay. So our designers are not trained for it. So that's why we are still going. And when I said wrong, I only mean that it is conceptually wrong, but practically it is giving us same design, safe design. Okay. How we manage it there, how that wrong method of design has been developed, okay, to give us safe design, okay, that also you will learn in this course. Okay, once you know the correct design, then you can compare it with the wrong design and see how we manipulate there, so that this wrong one is also giving us the correct result. Okay. So this is the crux of this course. Keep this in mind. Okay. We will stop here, and now we will be meeting on Monday. Monday. So Tuesday.